Now today is just going to be more about working some more examples with identities, using the kind of the principles that we talked about last time. Pardon me. So let's look at this. I think we got through the first three last time, right? So let's look at this fourth one. Again, our first principle basically is work with the more complicated side. Now this one looks equally complicated on both sides, right? Doesn't really matter. You want to work with the left or the right? Okay. Might as well pick the left, right? Doesn't matter. So there's lots of different things that you can try, generally speaking. But there's not a lot algebraically we can do to combine things at this point, right? I got a 1 and I got a cosine squared. So trying to put those two things together doesn't really help. Usually if we're trying to algebraically combine something, it's like down here at the bottom where we've got two fractions and we want to put them together, right? We'll do that one here in a minute. So there's not a lot of algebraic things that we can try. There's not really any of the convert everything to sines and cosines because it already says cosine, right? So really the only thing we can do is try to use one of our fundamental identities. And also, if you see one of the trig functions squared, you might want to think about what you can plug in for those particular trig functions, right? So in this case, I see a cosine squared. So what do you think we can plug in for cosine squared?
Oh, 1 minus sine.
Yeah, 1 minus sine squared. Good. That's one of the Pythagorean identities. Just rewritten, right? Probably the most famous Pythagorean identity, if you will, is sine squared plus cosine squared equals 1. Right? Do be careful with that, by the way. I do see errors a lot of times where someone will see 1 minus cosine x and just write sine x. That's all sorts of false. Okay? Don't do that. Okay? That's an equation to try to solve, not an identity at all. All right. So in this, if you see something with a trig, like I said, a trig function squared, think about one of your fundamental or one of your Pythagorean identities and see if that can help you start simplifying some things. Okay. What can we do next now that we've made that replacement? Yeah, let's multiply the negative 2 through, right? So you get 1 minus 2 plus 2 sine squared x. And what's 1 minus 2 equal to? Negative 1. And we can just rewrite that in the other order. And isn't that what we wanted to get to? Yeah. That was pretty short, right? But again, the main reason why I put this one on here is just the thought of, you look at that, I mean, it's a pretty straightforward example, really, but you look at that, I'm like, there is just not a lot I can do with it to start with, right? I can't combine anything. There's not a fraction to try to get a common denominator. It's already in terms of sines and cosines, so there's not a lot I can do. But I see that cosine squared. Let's try changing that out with 1 minus sine squared and see what happens. Because now we have actually an arithmetic operation we can do. We can distribute the negative 2 that we couldn't do before. That was why I put that one on there. Any questions on that one at all? If you look at number 5, what side do you think you might want to start with in number 5? The left, right? So work on that one for a minute. See if you can see what happens when you try to go through that one. But I would totally agree. Work with the left-hand side. See if you can make it look like the right-hand side. So what did you do first?
Combine like denominators or break like denominators.
Yeah, like get common denominator, right? It's probably the best thing to do to start, right? It's the whole reason why we wanted to work with that left-hand side first, right? There's something algebraic that we can do to combine on the left-hand side. It's a lot harder to try to figure out what to do with secant and break it back apart, right? So what would you multiply the first one by? Yeah, 1 plus sine theta. And the second one we would multiply by cosine theta. Cool, good. So far, so good? It's a good first step, right? So again, that's the whole reason why we chose to work on the left-hand side. It's because there actually is something, honest to goodness, algebraic to do. And honestly, most of the work in this problem is going to be algebraic. Okay? So for example, what are we trying to end up with? What do we want the last thing to be? 2 secant theta, right? Secant is the same thing as 1 over cosine. So I do want to see a cosine in the denominator, which I see in both of those, right? What do we not want in the denominator?
1 plus sine.
The 1 plus sine theta. So somewhere along the line, that better cancel out. Okay? So in particular, why I'm making a big deal out of that, don't multiply out your denominator. Okay? It's going to complicate things. Okay? However, you do want to multiply out your numerator. I'll leave the denominator as cosine theta times 1 plus sine theta. What do you get when you multiply out the numerators in your first fraction? Go ahead, sorry.
Well, I got 1 plus sine theta plus sine theta plus sine 2 theta plus cosine.
Yeah, you combine the sine thetas and you get sine squared when you multiply the other two together, right? Okay. And what do you get to when you multiply the cosines? We just get cosine squared. Yeah, so when you FOIL, distribute, whatever you want to call it, for the numerators, if I multiply my 1 and my 1 times my sine times my 1, and my sine times my sine, so that's what we get to that one. Again, that was just more algebra, right? There wasn't any trig at all. The next step, I think, is a step of trig. What do you recognize? Yeah.
Sine squared plus cosine squared.
Good. Yeah, that's one of the ones, but that's a big one you should recognize, right? Sine squared plus cosine squared, we can replace that with 1, right? So this part right here is replaced with 1. Add my 1 and my 1 together, I get 2 plus 2 sine theta. What can you do on top now? You can factor out a 2. Good. And what did we say wants to go? Try that again. What did we say we wanted to go away? And what happens? They cancel out. Good. All right, those go away. We see 2 over cosine theta, which really then is 2 secant theta. Honestly, a lot of what we do when we're verifying trig identities is algebra, right? There were exactly 2 steps of trigonometry in this problem. Here's step 1 in trigonometry. Here's step 2. Right? Absolutely everything else was an algebraic step. That happens quite often when we're verifying these things. And most of the trigonometry involved is recognizing one of your fundamental identities, be it a Pythagorean identity or a ratio identity, even odd identity, cofunction identity. Is that okay? Let's look at the next one, see what we got. Ooh, there's a good one. This one put on here for an example of what I talked about briefly on pardon me, briefly on whatever day it was, Wednesday. I forgot what day it was today. Trying to get there. We've got tangent of tangent of theta plus 1 over cotangent of theta plus 1 equals sine of theta secant of theta. Written kind of strangely, but that's okay. Which side do you think you might want to work on?
Left side.
The left side? Sure. There's more things going on the left side than the right, correct? However, just take a peek at the right side before we get started. How can you rewrite secant? 1 over cosine. So what does the right-hand side really look like? It's just tangent, right? You got sine over cosine on the right-hand side, don't you? So really what we're trying to get to is tangent. Then we can rewrite it to get that other piece. All right. So since I know that really I'm just trying to get to tangent, right? One of your first thoughts might be to change everything to sines and cosines. That's certainly legitimate, right? But I wouldn't change everything to sines and cosines to start with. I would instead use a reciprocal identity. This is not the only way to go about this, by the way. I would use a reciprocal identity to replace cotangent. How can you write cotangent in terms of tangent? It's just 1 over tangent, right? And again, the only reason why I did that was because I looked at the right-hand side ahead of time and said, that's really tangent. So let's just keep everything in terms of tangent and see what happens. Does that make sense? Okay. All right. Pardon me, sorry. To help us out here, this is a complex fraction. I'd like to clear the denominators. What could you multiply top and bottom here by to get rid of the denominator? What could I multiply top and bottom by to make this fraction go away? I could do a conjugate idea, but that's more complicated than I want for right now. I literally just want this. What do I need to multiply this by to make here's my tangent? So I can multiply both sides top and bottom by tangent and make that tangent go away. Let's not distribute out the top. However, distribute the bottom. What do you get when you distribute out the top but the bottom? When you take the tangent of theta and distribute it through, what do you get? Okay. That was the whole reason why we did it, right? To get rid of the fraction. Anything nice happen? That was loud, sorry. Yeah, the tangent plus 1's cancel, don't they? Hey, look what we're left with. Tangent. Which is, we already agreed that that was what we were looking for, right? So I know I said at the beginning, when we started all of this, is look at the more complicated side and make it look like the simpler side, which is exactly what you want to do. But also pay attention to that other side. See if it is easily rewritable into something that's a little bit more recognizable. In this case, sine times secant really is just tangent. So even though you could have attacked this problem by writing everything in terms of sines and cosines, it's probably a little bit easier to just say, oh, hey, I can just leave it in tangent because I really just want to get the tangent. You could have done exactly the same thing that we did here. If you did it in terms of sines and cosines, just to go off to the side here, I could have started this way. There's nothing wrong with starting it this way. I think it'll just take us a little bit longer to get there. Literally no problem starting it this way. And I would do the exact same next step that I did previously. I just have a different denominator. What would you need to multiply top and bottom by to make both denominators go away? I need a sine theta and a cosine theta to make the other one go away, all right? I need to multiply by both of them to make my fractions nicer. Okay. So you can do the exact same thing. Just takes a little bit more work, right? And then I think you need to refactor something afterwards. You'll get there if you follow your steps and do all the algebra correctly. You'll get to where you need to be. Okay. Just a little bit longer. That's why I said pay attention to what's on the right side too. Notice again, I probably know I mentioned this before. There's your one step of trig, really. Right? Everything else is algebra. Going on to calculus, you'll notice that the same kind of thing happens. In calculus, same kind of thing happens. You get one step of calculus maybe, and a whole bunch of algebra and trig steps. This one mainly is just to remember one of your factoring special form factorings. So you probably remember this one without too much doubt. What's that one? Yeah, it's a difference of squares. So you get, when we factor that one, what do we get? Yeah, a plus b and a minus b. Good. That one, everybody typically remembers difference of squares. You also have a couple for cubes. Again, I put this one specifically on there to remind about these forms. See, you think I might not put any thought into when I put these together. I really do. All right. Do you remember how the difference of two, the two look the same? Good grief, why can I not talk? The two look very similar to one another. You remember what difference of cubes looks like? That would be a plus b, the whole thing cubed. So this one's a little bit different. Oh, let me remind, so we're not all thinking for a long time and not going anywhere. Yeah, remember those now? Starting to come. So anytime you have a difference of something to a power like this, so notice that a squared minus b squared has a minus b in it. A cubed minus b cubed will also have a minus b in it. If you had a to the fourth times, or minus b to the fourth, it has an a minus b in it, and so on up the line. They all do when it's minus. Notice that it's a minus b here. The sign in the middle here is a plus. When you do the sum of cubes, the sign in the middle is a minus. Same format. Just a little bit different. The only thing that really changes is those signs. All right, which of those is actually relevant to the problem we're doing? Yeah, the last one, right? Because I see a sum of cubes on the left-hand side. All right, so how does the top factor using the sum of cubes formula?
plus 1.
Okay, that's tangent theta plus 1. Good.
And tangent squared theta minus tangent plus 1.
Good. Cool. Yep, that's exactly right. Your tangent theta is the A, your 1 is the B, right? Because that's tangent theta cubed plus 1 cubed. Notice again, no trig, right? That's an algebra thing. Kind of harping on that today, aren't I? I'm nothing if not annoying. What do we do now?
Tangent theta plus 1.
Good. So we're left with tangent squared theta minus tangent theta plus 1. Part of that's good. Part of that's what we're looking for, right? What part of that is good thing so far? Minus tangent, right? That's a good thing. So the other part must be what? What's left must be what equal to what? If I already have part of what I need, what must the other part be equal to? Secant squared, is that true? Yeah, if I look at this part right here, we look at that part right there, that is secant squared, isn't it? It's one of our Pythagorean identities. And we're done. There was your one-step trick for the problem. What questions do you have on that one? Is that all right? All right. See if you can work on the next one for a minute. And then we'll chat about it. Through it on the left as well when we're done. But I would absolutely start with the right versus the left in this one. Because again, like I've said all along, it's a lot easier to combine than it is to split apart. Not impossible, right? But think about just with numbers. What's easier, multiplying or factoring? Multiplying, right? It's easier to combine than pull apart, just generally speaking. As a matter of fact, as far as numbers go, internet security is based on the fact that factoring is hard. Dead serious. It's the entire crux of keeping things secure on the internet. Factoring's hard. Anyway, what do you do first then if you start with the right-hand side? Good. Make secant 1 into 1 over cosine, because now that allows you to do what? Get a common denominator and combine the fractions, right? So to get a common denominator, we should do what? Yeah, good. Good. So I need to multiply the second piece by cosine over cosine, right? So we get 1 minus cosine squared on top over cosine. We recognize anything about the top? Good. Yep, exactly right. Sine squared over cosine. Is okay so far? Now this might be maybe the trickiest part of this going through this whole side. I need to recognize this as what's on the left-hand side, right? But what is tangent equal to? Sine over cosine. Do you see a sine over cosine in there? Yeah, I can just pop out a sine over cosine and then have an extra sine to go, right? So you can write this as sine over cosine times sine. And then we really do have tangent times sine. Does that make sense? Okay. I said you could go from the left-hand side to the right basically this is what it would be. Just read this thing backward. Yes. Is that what you did? Was it backward? Absolutely. You could absolutely do it that way. Start here. Make this here. Multiply it. And now you have a sine squared, and we've done the substitution the other way around, right? Sine squared is 1 minus cosine squared. Break up your fraction and simplify. And you get back to where you started. Right? So you could have gone left to right, just take these steps and write them in the reverse order. They work exactly the same way. Questions on that one at all? All right. So this is, pardon me, playing around with verifying identities. We're going to create some new identities starting on Monday. We'll have to add to our toolbox as well. But before we do that, one of the things that we want to do is use Pythagorean identities to help us rewrite algebraic expressions without a radical in it. And this is a skill that pops up in Calc 2 in particular to be able to do this. Okay, so while we're doing this, it's also a nice application of your Pythagorean identities. So remember our 3 Pythagorean identities here. You've got sine squared plus cosine squared equals 1. Tangent squared plus 1 equals secant squared. I'm going to write the third one down again. We're not actually going to use this one in the other ones. I'll write it down. We're going to use the top 2 for what we're going to do here. All right. The goal of what we refer to as trigonometric substitution is to make the square root go away. What do you want to see under a radical if you want the square root to cancel? What cancels with a square root? A square, right? So what we want to do is make a perfect square under the radical. That's the whole goal of this trigonometric substitution. We want to make the square root go away. In order to make the square root go away, I need to see a perfect square in the denominator. Okay? So I'm going to take these, we're going to take these first 2 first 2 Pythagorean identities and rewrite them in a form so that I can see we substitute one thing out for a perfect square. All right, so the first thing I mean is let's look at this one. If I do 1 minus sine squared, we get cosine squared. Okay? So if I can write something with a 1 minus cosine squared in it, I can replace that with sine squared, and then I can do the square root. Okay? So let's look at this first example, and then I'll go back to the other 2. But let's look at this first example. Notice it looks like almost like this form, right? I've got this minus variable squared. Okay? Now you don't have to write this next part down because this next part's not going to work. We're going to have to adjust it, and I'll have you write that down instead. Okay? So what you might be tempted to do at this point is say let x equal sine of theta. Because it kind of fits that form, right? I want to do something minus sine squared so that I can replace it, right? The problem is with this, is that a trig identity? No. Okay. What would I need right here so that I could factor something out and make a trig identity? What would I need for a constant to see a 1 minus sine squared? Well, I still want to see a 1, right? You're thinking about it the right way. But I need a 1 minus sine squared. In order to see a 1 minus sine squared, it wouldn't be 1 over 4 I need there. I need a 4, right? I need actually, honest to goodness, 4 here, right? I need a 4 to factor out. right? Okay, so let's go back over here. How did I get sine squared? I squared the x. So what could I put right here so that I end up with a 4 there? Remember, we're going to square the x. So what could I put right there in front of the sine so that I end up with a 4 where I need it? A 2, yeah. So instead, let's make this a 2. So if we have x equals 2 sine theta, then we get, I'll write it out longhand to start with. I'll write it as 2 sine theta, the whole thing squared. That gives us 4 minus 4 sine squared theta. Again, the reason we like that is because we can now factor out the 4. And now I'm at square root of 4 times 1 minus sine squared theta. What can you replace the 1 minus sine squared theta with? Cosine squared theta, good. Oops. I said cosine and wrote an S. And now do your square root. Square root of 4 is 2. Square root of cosine squared is cosine. Technically, it's not just cosine. Technically, it's absolute value of cosine. Remember, square root of 2 squared is 2, but square root of negative 2 quantity squared is also 2. Okay, so technically you get the absolute value when you do the square root of a square. We don't typically write the absolute value here because we assume that our theta is in the first quadrant, so everything will be positive and we don't need to worry about the absolute values. But just technically know there should be absolute value bars there. That never ever comes up when you actually use this in practice to be able to do these problems. All right. So did you notice again, the reason why we put the 2 in here is so I can factor out that constant. Okay. So let's look at the next couple of examples that are in slightly different forms and see if we can play around with that constant idea again. Okay. All right. So let's rewrite the other 2. This is actually, I'm just going to rewrite this one in the other order. I'll write it as 1 plus tangent squared. Now, it doesn't matter. They're both the same. Equals secant squared. Or if you subtract, secant squared minus 1 is tangent squared. Notice the 3 forms. I've got constant minus variable squared, constant plus variable squared minus constant. Okay, that's what we're looking for in the radicals. Okay, looking at this next piece, which of those 3 forms do you think you might want to play with given what's underneath the radical? Do you want to use 1, 2, or 3 that's listed up there? 2, right? Notice the form is variable squared plus constant, right? A lot of math is pattern recognition, so we're trying to recognize the pattern we're going to use for the identities, okay? Variable squared plus constant looks like this one, right? So I want to use tangent in this case. So x will be something times tangent theta, okay? Again, I can replace 1 plus tangent theta, right? I can't just plug tangent theta in here because I would just have tangent squared plus 25. That doesn't tell me anything. I need to be able to factor off a 25. So what do I need to put in front of this tangent so that when I square it, I can factor off a 25? 5. Good. Yep, that's exactly right. So I'll let x be 5 tangent theta. So you get 25 tangent squared theta plus 25. Factor out your 25. What do we recognize tangent squared plus 1 is? Secant squared. And now how can you rewrite that square root of 25 secant squared? Yeah, 5 secant theta. Good. Does that make sense? Notice the reason, pardon me. The reason why we want to do this is because we want to make the square root go away. Notice I can't split up the square root over the sum, right? That's what's bad about this particular square root, is I can't split it up over the sum. That's why we're replacing the sum with a single term, so that we can make the square root go away. Now at the end, in calculus, you do something to this, and then you have to undo the substitution with a triangle. But this is all we're going to do for our purposes, is just doing this practice. All right, let's do the last one. And finish up the handout here. This one is variable squared minus constant of 1, 2, 3 that I listed up at the top of the page. Which one do you want to use? So with the cosine one, it was constant minus variable. This one's the other way around. It's variable minus constant. I better use the secant, right? Because they have secant squared minus 1 is tangent squared. When it's that way. Now again, I have to play with the constant, typically. I want secant squared minus 1 when I'm done, right? If I just put secant in, I get 9 secant squared minus 1. I want 1 secant squared minus 1. So what should I put in here to make the 9 go away in this case? 1 over, well, it needs to be 1 over 9 when I'm done, but I got to square it, right? So it should be 1 over 3. Yeah, I better put a 1/3 in front there to make the constant go away. So when you square the, goodness gracious. When you square the 1/3 secant theta, you get 1/9 secant squared theta, so the 9s will cancel. Secant squared theta minus 1 is tangent, good, squared theta, and so we just end up with tangent theta. That one okay? Yeah. Those are kind of fun to play around with. Basically, you're just trying to do pattern recognition, right? But those are the 3 patterns. Constant minus variable squared, constant plus variable squared minus constant. Okay? All right. Well, have a good one. We'll see you on whatever day that is, Monday. Have a good weekend, everybody.